Okay, so today we start this, we have been discussing about universal soil loss equation. The universal soil loss equation, that is, we have started the discussion on. We said that, in any case we can estimate the soil loss ton per acre per year by multiplication of number of factor RK, ALS, CP. We have already explained that this R means the rainfall factor, K is the soil erodibility factor, L is the length factor, S is the steepness factor or slope factor that we call it, and the C is the vegetation factor, and P is the mechanical soil erosion control factor. So, having said this, we were discussing about how to use this. So, I have already explained, this is in the class last, I was just talking about, how to actually determine the different rainfall factor. This is, we have already explained K is determination of K is explained, determination of K is explained. I have told you, I will again come back to that anyway, but before that we start into, so the R, determination value of R. I said that in most cases we use the iso-erodents that we use. With this iso-erodents, they have a large table. So, herein we will just try to bring this, in a smaller values, like in cases like India, the type, I said the type and value of R. Say type, the type is intensity and duration of rainfall in a geographical area, intensity and duration of rainfall in a geographical area, and the second one is, this one is rainfall factor. The rainfall factor here, the one we generally explain here is this, to start with, say between, say the higher values that 600, so say 625, so 625 to 600. I'm sorry, let me put it here. 625 okay, 600 to 625. Here this one is, try to understand this, high intensity, very high intensity and long duration. Very high intensity and long duration rainfall areas. The factor that we use is, the rainfall factor is about 600 to 625. Then it comes to, say very high intensity and medium duration, medium duration, the value we should be working on is between say 600 to 525. Okay. Similarly, so as you can further go on, very high intensity and say medium duration, this is, then you can see high intensity and long duration, high intensity and long duration, we find these values to be, the values would be about between 525, so okay, here okay, 525 to we have about 450, right. So this is, then comes is medium high, medium intensity and medium duration, medium intensity and medium duration, the value would be between, say, this one is 450 to about say 400. You see, not necessarily in the same proportion it would reduce. So similarly, this is say low intensity and long duration, low intensity rain but for a long duration. In such cases we can have it between 400 to 350. Okay, and here is low intensity, long duration, that is, then it says low intensity and short duration. So here is duration, we will have mostly the value between say 350 to 125. So in cases, that is, you can always use the median values, median values in cases like this. So in cases here, you can see for your case, there's usual value that we should take is between 610, then it is 5, say 570, then these values can be between 500, 425, 375 and also say 200, say 250. Okay. So here, these are the values you can start with to calculate. So this is the rainfall factor. So we have come to know that how. So what we say is generally, suppose if it is given like in a rainfall area, say particularly in a rainfall area, in a geographical rainfall area. Say, I was explaining yesterday that, we generally go by an isoerodents, like, we find that, in India, generally, say the Nicobar area, this particularly Andaman Nicobar area would be having the highest rainfall area, mostly highest rainfall. Then as we go towards the west, the rainfall would come down. So similarly, what we use this, from this isoerodents, we can find out the value of this rainfall factor, the rainfall factor. So suppose if it is given in a problem or any other places, if you have to start with a value, you just say high intensity and long duration rainfall, you should select the value of R as equal to 500. This is the starting value we start with. So this is, we have already found out R and K. We have already found out R and K. Now, having to say this, R and K, what we further get here is that this is the R and K. Once it is found out, then in the next is length factor, S is the steepness factor. Other things being same, you just, if you just, the nomograph that I have given to you, you just see here, say these values here, if you can finally, so let me explain here from this, the topographic factor LS, the values of topographic factor, L and S. You see here, suppose you have, all these values, this one is still in agricultural engineering, number of things are still in fit. So you find it like this, say here, suppose the slope length is slope length along the slope, it is about say 300 feet and having a percent slope, say about 10, okay, say percent slope about 10. So you can find out the value at see L into S equal to 2.37. Okay. Now here is, this is what is interesting here is, say is just in other cases, in case of C and P, generally if they are not applied, that is the vegetative factor is not applied, neither the mechanical soil erosion control factor being applied, in such cases the values are 1. But here all the while you can see the values can range from say highly fractional values like say 0.1, even 0.06 to start with, and can go up to 12.9. So remember this, so L and S together can be, L as S can be, the values can fluctuate from 0.06 to 12.9 depending on the situation. Now what happens is, apart from this, there are few other things to be explained here. Is say if L is given, S is given, you can find out the value of L and S. Okay. Now having to say this, now what happens here is, in cases like that, if it is an uniform slope, you can find out the L, you can find out the L like this, you can find out the L like this, okay, and that the slope S factor you can find out from this S factor percent. So from the percent slope you find out the S factor, L into S. In situations like where the slopes are in subplots like this, where this is L1, L2, L3, and each of them say having a different S and different S, as you can see, percent S, this is percent S1, this is percent S2, this is S3, S3. In such cases, we have to find out the combined LS for the slope, combined LS, In fact, it is not only combined LS, it is sometime this, if it is having the soil erodibility factor K1, say this K1 having this one having K2, K3, depending on the different soil types. Remember this. This is the slope parameter L1 and S1, length of the slope and the gradient of the slope. K1 is the soil erodibility factor depending on the soil structure, soil texture and permeability. So, if these things are variable, so in such cases we can find out combined LSK as L1 K1 plus L2 K2 plus L3 K3. Okay. L2 K3, and this is LSK. LS it is okay. I put the S1 here, S2, S3. So here, or else we can even conventionally you can write L1 S1 K1. This is all multiplied plus L2 S2 K2 plus L3 S3 K3. Okay. So here this is what is the combined LSK. So we have by now we have found out say 4 factors. The import these 4 factors we have come to know, that is R, we have found out R, L, S, K and their combined effect. Okay. Now, there are 2 things more we can have to find out. What is C, what is P, what is C and what is P. So, you can see this apart from not going into the much of the other things about LSCP. Let us the first part for the CP. What we find out here is, let us see this plot here. Okay, if you have brought it out, so here itself you just see this. What is the first of all? What is this? The mulch. If you remember, if you do not remember this, the mulch is, I said that the vegetative material that would be spread on the slope. The mulch is as I have said, wood cuttings. It can be sometime say raw hay, straws, that is hays after the paddy is cut. All this stuff would be generally spread onto the soil slope surface. This is just to reduce. I have explained that the importance of vegetative material in reducing the erosion. So this mulch, this is generally put in terms of say 1,000 pound per acre, 1,000 pound per acre. So suppose for a slope we have spread for a slope we have spread say 3,000 pound per acre mulch on top of the slope surface, on top of the soil slope. So it is 2, 3. You can see this. Say here 0, 1, 2, 3. So 3,000 pounds of material has been spread on the soil surface over an acre of area. In such cases, the percent soil cover have to be found out first. So here it comes, the percent soil cover becomes almost 80. Say let us keep this value as 79. If you see this, if try to see this again, according to this plot, this is where it is say about say 3. So it is more than, it is more than 80 here, say 82 or 84 like this. Okay, 84. If this is 84, right? This 84 has to be again brought back here. This is the percent mulch cover or percent soil cover. This one is 84. okay, you bring it down the 84, this becomes, the vegetative factors become point, say 0.075 or 0.078, isn't it? Say at 80 it is close to 0.1. So the value that I said, say about 84, it would be about say 0.8 or 0.9 like this. Sorry, 0.08 or 0.08 or 0.09 like this. So this way we can find out the value of this vegetative factor. Say for a lesser value, say if we have said we have spread mulches 1000 pound per acre. In such cases, you find that the soil coverage is only about soil coverage about 50. This 50, if you just plot it with this 50 here, the vegetative factors become 0.3. So what is interesting here to observe is, or important for all of us, that is when no soil, no mulching, nothing is being added, the vegetative factor is 1. When something is being added, the value is consistently going down. Yeah. So here this has to be watched and noticed on all the time. So here this is how we can find out the vegetative factor C. This is how we find out the vegetative factor C. So we have also found out C. We have also found out the way, we have also known the way the C can be found out. We have also known the way the C can be found out. Apart from that, then the next one is our values for mechanical soil erosion control factor. The mechanical soil erosion control factor. The mechanical soil erosion control factor is can be I think is somewhat not clearly visible, but you can see this if you don't have these values with you. Let me write down the values for you. The values for mechanical soil erosion control factor is slope percentage and P. Mechanical soil erosion control, the soil, and this one is the value of P. So the mechanical soil erosion control, they say say for this, like what we have been trying to do here is this. Say we are using say say typical the terraces and diversion ditches. This is the mechanical soil erosion control. We have used these terraces and diversion ditches applied as per requirement. If we have done so, terraces and diversion ditches, I have explained this in the last classes, what are all this, terraces and diversion ditches, if they are applied, say for a 1 to 2% slope, or say 3 to 8% slope, 9 to 12, 13 to 16, 17 to 20, 21 to 25, 21 to 25, say, and then say 25 to say 26 to say 30 and 26 to 30. So, this, if we can use these values now, see here the value of P here is 0.12, 0.10, 0.12 again, 0.14, 0.16, 0.18, and this one would be 0.2. What it means here is this, these factors, when there is no mechanical soil.
The first one is 0.12.
Yes.
Then again 0.10.
Then again 0.12. So here, this it goes on to say that effectivity is not similar. His effectivity is not similar. Effectivity varies according to the slope. Here this one is 1.2. If no soil erosion control then in case of this is, you have taken this down, this table. Yeah. In case you have not, in case no mechanical soil erosion control has been made, the value of P is equal to 1. Remember this, it never becomes 0 as such. 0 means everything comes to 0. It's nothing like that. If no mechanical soil erosion control has been made, the value of P is equal to 1. Now let us see a problem. Say now, say a problem or in a problem or assessment of a particular situation. Let us take a problem, a situation like this. In a long high intensity and long duration rainfall area, in a high intensity long duration rainfall area having percent silt and percent very fine sand, both this percentage together, percent silt, and this is additive actually, percent silt plus percent very fine sand having and of say 30%, of say 40%, percent sand, as 20%, percent sand as 20% with organic moisture, with organic matter, with and percentage of organic matter, or a percentage of organic matter being say 2, 2 percentage of organic matter is equal to 2, then very fine, say this kind of soil, very fine sands, it would be almost coarse granular, structure, coarse granular structure, and having permeability, moderate, annual erosion has to be calculated. If 2.5 if 2500 pound per acre of vegetative cover, also or the mulch cover, vegetative or mulch cover is given, and terraces are made for 15% slope and slope length say 200 feet. What will be the annual erosion by universal soil loss equation? Okay. So, remember, this is a barren slope. This is generally a barren slope. Say, it's particularly a freshly exposed soil, like what you find in overburden dumps, or say fresh overburden dumps, what we observe there. Or if we have not made this we have not done terracing, we have not done anything like that, and if we have done things like that, what is the effect? Say here this. So, what we are now, you see how we are going to find this out. Say high intensity long duration rainfall area, what would be our solution?
High intensity long duration 600 ton.
610, right? This is the 610. So, this is a basic value that we are just trying to find out. Say this is K, what would be K? Find out K. So, this as I have explained in the yesterday's class, let me again begin this. Say this K here, what we have said is silt and very fine sand as 40%. Okay. So, you see this plot here 40% here, you just see this is 40%, and we have sand as 20%. sand as 20%. This is the 20% curve for sand. This is 20. So here 40 is going to be connected here in this case. Okay, it is being connected somewhere here 40 and this one. You can see this. Okay, now this is not enough. Now this is not enough. Then from here, from this point where it has connected, from the point where it is connected, you have to combine these two. You have to combine these two. You have to find out, if you just extrapolate this value, you have to find out the value of at organic moisture. What is the value at that organic moisture is, organic matter that I have said is 2. So there's 2. If you just connect this line 2, it comes to the first approximation value of about 30, isn't it? So what you have done is, let me repeat it again. This is 40. This is 40 is this one is the 20 here that I have said. So 40 and 20 getting connected here at this point. We have just extrapolated it to 0.3. 0.3 is the approximate value of K. This is approximate value of K. This 0.3 should be further extended here. So for further refinement of this, see now here, this one is 0.3. This 0.3 is finally getting connected. I said the structure of the soil, as I have said, is coarse granular, isn't it? 3. So this value of 3 here, it comes to 3. So here, this is where this value is. This is where it is getting connected. See this 3 getting straight away connected at 3 here, at the intersection point with the dotted line. Can you see? Yeah, so here from this, at this point, say here, if you just try to observe this, say now this 3 gets connected with 3 media, this one 3 medium or coarse granular, 3 medium or coarse granular, just about this point, say this is 3 and this one, isn't it? If you just find the point, say if you just drop it down, in a similar line like this, we have said that the permeability is 3, moderate, isn't it? So this permeability is 3 means this firm line here, say about this 3. So this 3, if this 3, it would again come back, say about 0.29 or 0.28 would be the value for the K. We take another left turn from here. So we find out the soil permeability, soil erodibility factor K. See, let me explain you this first. The value that we have got 0.3 is the first approximation factor K. That can be further corrected with the use of the structure and the permeability. And whatever value we get after that would be close to this 0.3, but would be somewhat different. Say it is 0.3 here, it may be 0.29 or it may be 0.31 like this. So this is the value of K that we have to accept. That is the value of K we have to accept. So the corrected value of K has to be accepted. So this is called the soil erodibility factor that we will find out. You will also find out the value of K. So here it is, say the soil erodibility factor that we have found out here is about say 0.29. Okay. All right. Now here say RK, then we find out L and S. L and S, in such cases we have used only one slope, so you have to have a very, you don't have to be much worried about this. So percent slope is about 16. Says I said 15%. Let us say about 15. Say 15, and this one is, we have said about 200 feet. So 15 and 200 feet. The LS becomes 4.01, isn't it?
Yes.
It is 4.01. 200 here, 200 here, and 200 here. This value becomes 200 here and 16, which is about 4.01. 4.01, which is about 4.01. If you just see this again, relatively somewhat larger than this. So 16 and this is 4.01. So it is not 16 in our case. So let us consider that to be say about say between 3.25 and 4.01, the value between somewhere between that. So it is about coming out to be about say 75. So about 35 if you can add 3.6. Okay. So we find this as LS as equal to, as I have said, 3.25 plus 4.01 divided by 2. So it is about coming to say 7.25, that is about 3.6, is it? 3.63. About that? No, 3.25 and 4.01 divided by 2. So it comes to about say 3 point. If we could get a better value, you can find it out. Yes, okay. Now the C, next is C. How I have already explained you to find out the value of C here. The C is this. C is a percentage mulch cover. Percentage. Say the first one is, I have said the mulch that has been spread on that, effective mulch that has been spread is about 2,500 pound per acre. So it is here 2,000 pound. This is the value, this is the point where you find 2.5.
Yes, sir.
Okay. So 2.5 means, 2.5 would means about 80% of the percent soil cover.
Yes, sir.
This 80% of the soil cover, as we come down here again, about 80, we found the value about 0.1. 0.11. Okay. So C is 0.11. Okay. The next is P. We said that excuse me. We said that there is certain kind of say mechanical soil erosion control has been made, or is considering that the mechanical soil erosion control measures have been taken for this slope, which is about say so the slope we have said is about 15% slope. For this 15% slope, you can see this, the value, this is between 0.14. Considering that mechanical soil erosion control factors have been used, that is mechanical soil erosion control has been used, considering adequate has been made. So this P becomes 0.14. So if you multiply this now, so annual soil loss by universal soil loss equation is RKLSCP. So this one is R is 610, K is we can find 0.29, this is LS is 3.63 multiplied by 0.11 into 0.14. So this the value, that is what we get. So you can find out the value is, this one is the value, whatever the value that comes out in terms of tons per acre per year. We can compute, we can calculate the annual soil loss. This annual soil loss provides us the first estimate of how much soil loss is going to take place in a freshly exposed slope, or a slope which has been standing for say 1 or 2 years and the diversion terraces and ditches are made. This gives quite a good first approximation. Okay. So this has a lot of engineering application actually. This is how we can find out the typical soil loss, expected soil loss in a slope. expected soil loss in a slope. So with this, the soil part is mostly covered, for this course. There are few more things about soil to be told, but considering that we don't have much time left, so here there are few other things for your general reading. I would say please read the soil contamination. By soil contamination, the soil contamination particularly of the triad of metals that we are generally very we remain Ni and copper. This is also a great problem in most of the construction areas, mining areas. The enriched percentages of lead, nickel and copper, particularly in say metal forming rocks and minerals. And surrounding area. Okay. I would just ask you to suggest reading for this. Soil contamination is also a great part that needs to be explained. Okay. With this, the soil part is covered, so we will come back to air pollution in the next class. Okay. Thank you very much.
(1951). A young nation aspiring to find ways to fulfill a dream lays the foundation of an institution that will give aspiring technocrats the license to fly high. The first Indian Institute of Technology is born at Kharagpur. Founded on the basis of the recommendations of the N.R. Sarkar Committee that was set up in 1945 to consider the development of higher technical institutions in India, the institute was first established in 5 Esplanade East, Kolkata, before it moved to Kharagpur in 1951. With Sir Gyan Chandra Ghosh as the first director and Dr. B.C. Roy as one of its founding guardians, the institute established itself as the symbol of a young, dynamic and resurgent nation. As top students rubbed shoulders with the most celebrated of professors and scholars, visions took shape. And IIT Kharagpur continued to play the pioneering role that was envisaged for it, enabling India to become a knowledge powerhouse that it is today. At every stage of its evolution, IIT Kharagpur remained ahead of its times. It provided the best of facilities for the budding technologists, helping them shape their own as well as the nation's future. Indeed, today, IIT Kharagpur has blossomed into a time-tested, venerable institute of learning. With the rich experience of converting individuals into brilliant professionals through 50 glorious years. As you cross the campus gate, you feel the distinct nip that is IIT Kharagpur. The spirit of objective inquiry and lateral thinking hangs heavy in the air. The modern township-like campus of IIT Kharagpur, set in sylvan surroundings, is self-sufficient in all respects. From modern banks to the good old post office, from vast playgrounds and well-equipped gyms to modern auditoria and open-air theaters. And from the quiet fiber optic linked residential quarters for the faculty to the web-enabled hostel rooms for the students. At IIT Kharagpur, lush green bowers of tranquility coexist with smart cards and ATMs. Spread over 690 hectares of sprawling cyber habitat, 120 kilometers from Kolkata, IIT Kharagpur is one of the largest network campuses in Asia. Just the academic complexes itself spreads over a built-up area of about 2 million square feet, of which 150,000 square feet is the new complex that commemorates the Golden Jubilee celebrations. And that's not all. It is the only IIT to have conquered territory beyond its own through cutting-edge courses offered in its extension campuses at Kolkata and Bhubaneswar. IIT Kharagpur is not just about its large campus, but its diverse range of activities. It offers the widest spectrum of disciplines, ranging from aerospace, biotechnology, cryogenics, to architecture, mining and agricultural engineering, supported by strong faculties of sciences, humanities and management. There are more than 30 departments and centers that offer the largest number of undergraduate and postgraduate courses amongst the IITs. The courses are ever evolving and show the way for other sister institutions. The richness in its diverse activities is showcased by the technological support the institution provides in areas like architecture, agriculture, post-harvest technology and medical sciences. The institute has revolutionized and popularized rice milling technology. The other major contributions of IIT Kharagpur have been in the critical fields of defense, railways, space research, power systems and petrochemicals. All these activities directly empower the human requirements of the nation. Advanced facilities at the Institute make it possible to undertake cutting-edge research and service-sponsored research projects. The array of equipment ranges from aerodynamic testing laboratories to intelligent machining centers, atomic spectrometers, to VLSI design labs, molecular beam epitaxy, to anechoic chamber, fast protein liquid chromatographs, to liquid nitrogen plants. The cutting-edge technologies are at par with the best research facilities across the globe. In fact, the volume of research and development activities at the Institute is incredible. In terms of the number of patents it owns, the volume of industrial consultancy it provides, and the revenue that it earns from all these make IIT Kharagpur a class apart and strengthens its position as the true pioneer in technological education in India. The Institute Library deserves a special mention. Fully web-enabled, it is one of the largest in Asia with over 324,000 volumes of material, including books, videos, microfilm, and patent documents. ingredients that ensure a student's mind develops at the right pace. Along with its strong sense of academics, which is ensured by a strict selection process, life at Kharagpur is a celebration of, well, life. And at its heart are the students. In fact, the saying goes that you can take an IITN out of KGP, but not KGP out of an IITN. You've left a part of you behind. For most of the students, life in the campus was in itself a festivity, a collage of activities that shape their mind and body, a collage of events that was a synthesis of competition and cooperation, a collage of interests as diverse as dramatic.
आदर्शाय प्राणदास्मह्वयम् योगकर्मसु कौशलम् योगकर्मसु कौशलम् योगकर्मसु कौशलम्.
Indeed, in this golden jubilee year, as the celebration continues, Pandit Nehru would surely have been a proud man today. For him, IIT Kharagpur was always more than just an institute of technology. In his own immortal words, it is indeed a fine monument of modern India.